So we just went through a very broad overview of flexural members, what limit states we're going to eventually learn to investigate for a beam. And now I'd like to start by talking about one of those limit states in more detail. And we're going to start with the yielding limit state. And when I talk about the yielding limit state, I'm really referring to the plastic moment. So to learn more about this, I'd like for us to consider a really stocky beam. So a beam with a cross-section that has really stocky flanges and a really stocky web. Something that isn't going to be susceptible to local buckling. So there's our really stocky beam. And remember, we term really stocky cross-sections as compact when we're talking about flexural local buckling. This section is also continuously laterally braced, meaning it's not susceptible to lateral torsional buckling. And we're going to load this beam, hypothetically, until it reaches its full plastic moment. To do this, we're going to make a series of assumptions. I'm going to assume that moments are applied in a plane of symmetry of the cross-section. I'm going to assume that there aren't any axial loads to consider acting on the cross-section. I'm going to assume that as the beam goes through bending, that plane sections before bending remain plane after bending, and that's Navier's hypothesis. You probably talked about that when you were discussing flexure for the very first time in basic strengths. We're going to be working on the assumption of an elastic, perfectly plastic, stress-strain constitutive model. So I'm assuming stress-strain behavior that looks like that, where the break in this stress-strain behavior occurs at the yield strength of the material. And then I'm assuming that the material being used has identical stress-strain behavior in tension as it does in compression. So I'm assuming stress-strain behavior like that in tension and stress-strain behavior like that in tension. And this is a pretty good assumption for steel. Okay, so here is our cross-section. I'm using something that's very compact, and I'm looking at a cross-section that is rectangular in shape, so very simple. And we're going to load this beam with a value of P. So under this load, I have moments that develop in this beam. So if I were to take a break through this section, I would have an internal bending moment. Oops, let's see if I can draw straight. There we go. Here's my section. There's my bending moment that would be occurring. And I would have shear acting like that. So let's draw the flexural stress distribution acting on that cross-section's face. And I'm going to kind of expand this so that we can look at our flexural stresses a little bit closer. Okay, so there's my zero stress line. Going to have stresses that are in compression on the top fiber because the beam is in positive bending. I'm going to have tensile stresses on the bottom fiber. So there are my compressive stresses. There are my tensile stresses. Stresses are zero at the location of the elastic neutral axis. Okay, I'm going to increase the load a little bit. So the load is now larger than it initially was. I'm going to look at the stresses acting on my cross-section. Let's say I applied a large enough load such that the compressive stress is equal to the yield strength of the material. Since this cross-section is doubly symmetric, my tension stress is going to be exactly the same. So both of the fibers at the extreme ends of this cross-section are at the yield strength of the material. The distribution between those two stresses is still perfectly linear because this is a linear elastic material. So the definition of the moment that is produced by this particular unique force is called the yield moment. So the moment that produces first yield in the cross-section is the yield moment. So we're going to refer to the yield moment as M sub y. Now don't get confused, because sometimes we will talk about weak axis bending moments and also refer to those as my. And this is just one of those little idiosyncrasies that you see throughout engineering. You see the same terms being used to mean different things. When we use it in this context, it means the yield moment. So here, if you want, we can write M yield. So how do we determine the yield moment strength of the beam? Well, let's look at our bending stress expression. If I'm calculating stresses about the strong axis, that's equal to the moment being applied about the strong axis of the beam times some distance y from the neutral axis to the fiber of interest along the cross-section divided by the bending moment of inertia of the cross-section about its strong axis. So this is general bending stress. So a specific bending stress at first yield could be calculated using the yield strength of the material, F sub y. And so that would be corresponding to the yield moment, would be the particular moment that produces that stress. And since it's occurring at the extreme fibers, our very specific form of y corresponding to an extreme fiber is the variable that we call c. And that would still be divided by the strong axis bending moment of inertia. So this is the bending stress at first yield. And this is occurring in an extreme fiber. If the cross-section is doubly symmetric, it'll probably be occurring at top and bottom at the same time. So I can rearrange this expression to solve for the moment that produces first yield, M yield, or My. And that's equal to the yield strength of the material times the bending moment of inertia divided by the distance from the neutral axis to the extreme fiber. And this is the moment producing first yield. Now this term, Ix divided by C, we've seen before. This is just a section modulus. So I can rewrite this yield moment into the form that we're going to use most often. My is equal to the yield strength of the material times a section modulus. All right, so that's the yield moment. Let's see what happens when we increase the load above the yield moment. So now I'm applying a load much, much bigger than what we started with. What happens is now that we're above the yield moment and on the stress strain curve, some of my fibers are going to be in this elastic region, and some of my fibers are going to be strained beyond the yield strain. They're going to be plastic at this point. So if I look at the compression region, I'm going to have a segment of the beam that has yielded in compression to a certain depth. I'm going to have a segment of the tension portion of the beam that has yielded in tension. So looking at that on a cross-section view, I have some fibers that are completely yielded in compression and some fibers that are completely yielded in tension. So we're going to sketch that on a stress profile. So here I have my compressive stresses that equal the yield strength of the material, and here I have my tensile stresses that equal the yield strength of the material. And those extend to some depth. So this depth is equal to this depth. Then in between those yielded portions, the material is still behaving elastically. So between those two yielded portions of the stress profile, I'm going to have a straight line variation of stress. Okay, so what happens when we increase the load pretty much as big as we can make it? So the absolute limit of the load that we can apply would yield all of the fibers above the neutral axis in compression, and it would yield all of the fibers below the neutral axis in tension. So now every fiber along the depth of this cross-section has yielded. So if I look at that on my cross-section view, there are all of my compression fibers yielded, and there are all of my tension fibers yielded. The definition of the moment that exists in the beam at this point is called the plastic moment. So let me sketch the stress profile for this state of stress. All of my compressive stresses are at the yield strength, and all of my tensile stresses are also at the yield strength. So there's all of my compression stresses, yielded all the way through the depth, and then at the neutral axis, they switch to tension, but they are also yielded entirely through the depth. So again, the moment internal to the beam that produces this state of stress is called the plastic moment. So I'm going to spell that out. The moment that yields every fiber through the depth of the section is termed the plastic moment. We call it the plastic moment because all of the material through this depth is acting plastically. None of it is elastic. So really, what happens when we form this particular mechanism is a hinge. None of the fibers is capable of forming a moment couple with another fiber because they're all acting perfectly plastic. So in actuality, for this particular beam, we would have created 3 hinges in a row, and this beam would now be unstable. So that is the limit state of a plastic moment. It's the creation of a plastic hinge. Well, we went through mathematically how to define the yield moment back here, and I'd like to go through a similar process to define the plastic moment mathematically. So let's do that on our next slide. And I'm going to create a sketch of the cross section that we've been looking at, which is rectangular. So we're calculating this plastic moment capacity for a particular case right now, for the plastic moment. Here's our neutral axis. Since we were looking at the case of positive bending, fibers above that neutral axis are yielded in compression. fibers below that neutral axis are yielded in tension. So if I draw my stress profile, there are my compressive stresses, there are my tensile stresses, and they're both equal to the yield strength of the material. Now these stresses are actually acting over the width of this cross-section. So my cross-section has a width that I'm going to call B, and it has a height that I'm going to call H. So these stresses, Fy, are acting over the width of this cross-section. So if I draw that in 3 dimensions, this is actually acting over the width of my section B. And the same thing is happening in tension. I can find the centroid of the portion of this shape that's resisting compression. It's going to lie right there. And the centroid of this shape that's resisting tension. It's going to lie right there. And I can also sketch the force resultants on my stress block diagram. So there's my compressive force resultant. And here is my tensile force resultant. Now one thing remains true throughout structural engineering is compression has to equal tension. Equilibrium must hold true. I can calculate either of those forces. They're going to be equal. The tension force has to equal the compression force. And each of those force resultants is going to be the volume of the stress block. So I will color in the volume that I'm calculating. The volume of that block is going to be equal to F sub C. So let's calculate that. It has a width of F sub Y. It has a depth of B, and it has a height of H over 2. So I have Fy times BH over 2. Now to calculate a moment for this state of stress, it's going to be a force couple times the distance between them. So the distance between my compressive force and my tensile force is that distance. So I can calculate this distance is H over 4, and this distance is H over 4. So that total distance between FC and FT is H over 2. So again, my plastic moment is going to be a force couple times the distance. So it's going to be the compression force times that moment arm. Let's call this moment arm A, which has to be equal to the tension force times that moment arm A. So we said our force is equal to Fy BH over 2. And the moment arm, A, in this case, for this geometry, is H over 2. So let me be very clear about what we just calculated. This is a force, and this is a distance. So for this shape, my plastic moment is equal to the yield strength of the material times BH squared over 4. I'm also going to be very clear that this is for a rectangular cross section. So this is a specific application of the plastic moment, but I can generalize this. This is a geometric term, and we're going to term that Z sub x our plastic section modulus. So once we figure out how to calculate a plastic section modulus for any shape, I can calculate a plastic moment for any shape. So if I want to write this expression for plastic moment in generic terms, the plastic moment is going to be the yield strength of the material times my plastic section modulus. For a rectangular shape, we just found that Z sub x is equal to BH squared over 4. For other shapes, we'll have to learn a little bit more about how to handle this.